Thank you for the opportunity. This is also my first BOINC workshop. I am Greg Childers. I'm an associate professor in the Department of Physics at Cal State Fullerton, and I've been running the NFS at Home project for a number of years. This project is sponsored by the computational time provided by the Access project at the National Science Foundation. All right. So the purpose of the NFS at Home project is to encourage the continued development of state-of-the-art tools for factoring integers. And by factoring integers, I really just mean factoring composite numbers into their prime factors. An example is 35 factored into 5 times 7, or a more recent computation performed on NFS at Home is 2 to the 1091st power plus 1 factors into these 5 prime factors. So why do we want to do that? Well, first of all, factoring a number into its prime factors is a fundamental problem in mathematics. In mathematics, for any integer greater than 1, we know that that integer is either a prime number or it can be expressed as a product of prime numbers in a unique way. But finding those prime numbers for a general composite number is a very, very hard problem. But it also has applications, both in many, many areas of mathematics in which you require the factorization of a number to complete a mathematical algorithm, but also in computer science. It's a driver of research. There's both in classical computer science, but also quantum computer science. There's been a lot of work in the past on custom hardware to accelerate the factorization of integers, and also on quantum computers, the Shor algorithm to factor a number using a quantum computer would be a significant breakthrough once quantum computers become large enough. We have, not personally, but the Shor algorithm has been used to factor 15 into 3 times 5, but nothing much above that. 35 was attempted, but unfortunately it failed using that algorithm. And then practically, the difficulty of integer factorization provides the security for the widely deployed RSA cryptosystem. Basically, the public key in the RSA cryptosystem consists of a large composite number that factors into 2 primes. If you can factor that composite number into those primes, you can readily generate the private key corresponding to the public key and use that private key to decrypt communications. So factoring a large integer corresponds directly to breaking the RSA cryptosystem. For that, we use the number field sieve. That's what NFS and NFS at Home stands for. The number field sieve can basically be broken down into 5 steps, 2 of which are very computationally intensive. The most computationally intensive is the second step, sieving for relations. And that is the portion that we use BOINC for in the NFS at Home project. Basically, that step corresponds to sending work to clients within the BOINC framework to collect what we call relations. That is a factorization of simpler numbers that are constructed using the polynomials generated in the polynomial selection step. That is ideal for BOINC because there is a large amount of work to be done there. It is trivially parallel. We can just send different regions of the parameter space of search to different users within the BOINC network. It is sampling certain parameter space over a much larger space, so we can tolerate missing results. This means that we don't have to worry about, for a particular integer, the long tail. We can simply cut off work at a certain point and ignore any missing results from the long tail for a particular integer. Also, the relations that come back are quite easy to check, and we can easily invalidate work units that return bad results, and we can easily discard those results from the further computation. Also, because of this ease of checking the results, we work with a replication of 1. We do not resend work units. We don't use a wingman approach. We simply check the results coming back from each individual user. And then once we have a large collection of relations for the recent computation we've done that corresponds to, if we store them in a flat text file, we compress that text file. For the last number we ran, that corresponded to a 300 gigabyte compressed text file. We then take that collection of results from BOINC and then go into what on the client page I just call post-processing. We're just completing the last 3 steps of the algorithm. That corresponds to taking those relations and constructing a matrix, and then finding a set of vectors, non-trivial vectors within the kernel or null space of that matrix. For that computation, that's also the second largest part of the step that required computationally, second largest part of the computation. And that uses computational time provided by Access from the National Science Foundation. It used to be the Exceed project, was recently renamed to the Access project. One of the ongoing challenges for this project historically has been balancing the results coming out of the BOINC users with the available computational time on Exceed or Access. In fact, there's a little bit of time there in which that became particularly tricky. The BOINC project actually became a little bit too big, and we were running into issues having sufficient time on supercomputers to solve the linear algebra. But we've solved that problem, and we'll talk about that next. So a little bit of a history of the project. I started becoming interested in this in 2008. I wrote what was then a TeraGrid grant. TeraGrid became Exceed, became Access, to explore the limits of software that was available at the time. We factored the number 12 to the 241st power minus 1. That's now a trivial computation. We can do it at NFS at home in less than a week. But for then, the tools that were available were much inferior to what we have now. And then in 2009, a new library for doing number field Sieve factorizations was started, and that's called the Sieve library. And that's where I've spent the bulk of my time developing that code, along with others. In the same year, the RSA-LS BOINC project was launched. That's the RSA Lattice Sieve project. The project is a bit infamous because it was developed to perform the sieving, to do number field Sieve factorization of numbers that were used in the public key to sign the bootloaders of certain Texas Instruments calculators. This became a bit messy. Texas Instruments did not like this, and cease and desist letters were involved. The Electronic Frontier Foundation got involved on a pro bono defense of that project. But they went on to factor a number of less controversial numbers over the years. I contacted them. For me, they served as a proof of concept that doing the sieving step of the NFS algorithm over BOINC was feasible. So I contacted them, asked them about details of how they set up the project. They were very generous with their time, with their information. I improved on their framework and launched NFS at Home in 2009. In 2010, the linear algebra step in MSIV was significantly improved. We were able to make it more parallel across nodes using MPI. Just a note here, we cannot use, although there are a lot of general linear algebra libraries that are available, because of the nature of the matrix and the number field sieve, we can't use them. The elements of the matrix in NFS are, the entries of the matrix are elements of the number field F2. Basically, they are either 0 or 1. So any non-zero element in our matrix is a 1. Also, our matrices are very, very large. On a computation I have running right now, and the matrix has about 150 million rows and columns, with about 120 non-zeros per column. Also, those non-zeros are not distributed in any computationally friendly pattern. They're fairly random throughout the matrix. And so this is a problem that cannot be solved using standard linear algebra libraries. We have to write our custom code. So in 2010, we were able to add MPI parallelization, and that significantly increased the size of the numbers that we were able to tackle. In 2011, using that, we factored our first kilobit special number field sieve number. We factored 2 to the 1031st power minus 1. It was a pretty big breakthrough for the project. In 2012, when there was a major app upgrade, the author of the project that we used to collect the relations that the BOINC users actually run put out a new version that significantly expanded its capabilities. So we upgraded all of the apps at the time. The same year, RSALS shut down and they merged their user base into NFS at Home. And we also, a little badge I'd like to brag about, in Donald Knuth's text, The Art of Computer Programming, in Volume 2, there is a research level problem that is basically a number field sieve factorization, breaking RSA encryption for a small paragraph that he produced within the book, and we completed that project in 2012. So the latest versions of TAOCP acknowledges the NFS at Home for solving that problem. In 2013, we had a server upgrade. Before this, the project started on one of the desktop computers in my electron scattering lab. I'm also an experimental physicist. And that, of course, became quickly overwhelmed. We actually got a proper server in 2013, and that's still the server that we're using today. It's showing its age in some ways, but we're still using that server today. And then on this history timeline, you'll note there's a large gap between 2013 and 2021. At that time, the project was pretty quiet in terms of communication with the public. If you look back through the notices, you may have noticed public notices to users decreased significantly. There was no outreach, there was no public relations for the project. The reason for that simply became the fact that the project was becoming too big. We were returning results from the users faster than we were able to solve the linear algebra on the supercomputer clusters. And we simply didn't have room to grow. In fact, we've grown a little bit too much. But then in 2021, we were able to redevelop the linear algebra step in the MSIF library to use GPUs. And that was a significant breakthrough for us. What used to take 1 to 2 months to solve can now be done on the order of 2 to 3 days. Right now, I have a linear algebra run going on the Delta cluster at NCSA. That the 150 million by 150 million matrix running on 8 A100 GPUs, that's taking less than 3 days to solve. So that limitation for the project has completely been eliminated by the move to using GPUs for the linear algebra. So now the limitation for the project really is just based on what the server can handle. We do need to upgrade our server infrastructure fairly soon. So getting into the challenges. Challenges are those you've heard time and again at the workshops about using BOINC in general, time and resources. On the time side, I am the sole admin for the project. I do have a number of contributors who also help with some of the administration tasks, but I am the sole admin for the project. I've been leading the project since it started. Some of the things that are on the to-do list and have been on the to-do list for a while are to port the app, the Mac app, to use the new M1 and M2 processors. That hasn't been done simply because I'm not entirely sure it's going to be a net win. There's a lot of hand-optimized x86 64 code in the app on Linux and Windows in the current Mac app, and using the generic code path compiled on for M1, M2. I'm not sure that's going to be a net win, but it's something we need to try. There's also recently, this past year, been some work on the application to incorporate use of AVX 512. And so I do need to spend some time, perhaps this summer, taking a closer look at that code and seeing how well I can get it to run within the BOINC apps themselves. The website improvements, the website looks just as it did when I launched the project in 2009. It is in desperate need of an overhaul. I just haven't devoted the time to do that. And then recruiting and public relations. Even though the project does now have room to grow, that the linear algebra has been ported to GPUs. I'm still a scientist, and I still don't like doing recruiting and public relations, but that's something that we do need to spend more time on now that we do have the opportunity to grow. And then on resources, the server is now 10 years old. It's a single Dell server. It's showing its age in a number of ways, so I do need to spend some time coming up relatively soon recruiting some grant money to do an upgrade for the server for the project. But I just wanted to give you, in the time allotted, a really quick overview of the project. Thank you for your time, and I'm happy to answer any questions that you might have.